In the last lecture, we could see that the transfer function can be obtained from the impulse response function. Now, I would like to show you another way when we have got the state space equations of a system and we would like to get the transfer function. So it's easy to show you it through an example, and this is the state space representation of a problem. And first we have to derive the Laplace transform of these equations. We have studied a rule for the derivative. So if we have got the Laplace transform of x1t function, and we have got the x1 dot, and we would like to Laplace transform it, it means just a multiplication of s. So S1 and S2 will be on the left hand side of the first two equations and y on the last. So I use capital letters because of the transforms. So, and I just copy the right hand side, minus 2x1 minus 4x2 plus u, minus 4x2 plus 2u, and 3x1 plus 2x2. So these are the equations in the Laplace transform space. These equations, as you can see, these equations are simply algebraic equations. So now we have got a system of equations with three unknowns, and the unknowns are x1, x2, and y, because the input u can be supposed to be a known function. So from these equations, we have to carry out y over u. This is the goal of our calculations. I'm going to use different colors. For example, for the first, we can go with the second equation because it's quite simple to see that it is s plus 4 multiplied by x2. It is equal to 2u, and from this equation we can get x2 as 2 over s plus 4 and u. This is x2. Now I am going to go to the first equation, to here, and I am going to pull this term to the left. That's why we can write s plus 2 x1. This is equal to minus 4x2, and I am going to put it to here. So this will be minus 8 over s plus 4u. This is minus 4x2 plus u. So we can write the following: s plus 4 in the denominator, minus 8, and s plus 4 in the numerator. And finally, this will be s minus 4 s plus 4u. So this is that we can obtain at the end. And from this, x1 will be s minus 4 over s plus 4 and s plus 2 in the denominator, and this is multiplied by u. So the first two equations have been solved. x1 and x2 can be got as a fraction. The first is very simple, the second is a little bit more difficult, but it is multiplied by u. And there are something in the numerators and in the denominators. And now I'm going to use red to go to the last equation, to here. So y is equal to 3x1 plus 2x2. we are going to write the following. 3x1 will be s plus 4, s plus 2, and I have to multiply the numerator by 3, and I just say it's 3s minus 4u. Plus 2x2, this will be 4 over s plus 4u. So this is the equation for the output. Let's do the following. Make the same denominator. This is s plus 4 and s plus 2 and 3s minus 12 plus 4, and this 4 is multiplied by s plus 2. This will be u. Okay, let's go. S plus 4, s plus 2. So this is 3s and 4s, it is 7s. And minus 12 and 4 by 2 is 8. It will be minus 4. And finally u. So this is y. And we need the transfer function. The transfer function is, by definition, is y over u, and this will be 7s minus 4 over s plus 4 multiplied by s plus 2, or in another form, by polynomial over polynomial, we get 7s minus 4 and s squared plus 6s plus 8 here. So these are the transfer function of this system. So from the state space equation we have to get an algebraic equation, and again I would like to highlight it is an algebraic equation, and the work with this algebraic equation is very easy. As you can see, we have to focus on the output transform y. It should be equal to this one. This should be equal to something which is a transfer function and u, and from this equation we can obtain the transfer function very easily.